wrapping errors in the loop closure. So this is an example of a good loop closure that we don't need to go with the removal. Yeah. And this is so next is a small baseline inversion. So after we ensure that all the bad interprograms are removed, we can ingest the remaining interprogram into the small baseline inversion. This is the core part of the algorithm. This is where we estimate the time series displacements and finally the velocity. And so how does the SPAS or the small baseline inversion works? So as you see here, LiCSBAS employs an SPAS inversion algorithm. So what is LiCSBAS inversion? So first I will explain the traditional SPAS algorithm and what the limitations that we had in the traditional SPAS algorithm and why LiCSBAS tries to use the LSPAS version. So here, this is a normal SPAS that we have. So in one side, we have M unwrapped interprogram as our observation. These are the observation vector. And on the other side, we have the incremental displacement, which are n minus 1 incremental displacement. So these are the observation, the unwrapped data, and these are the incremental displacements. On the other side, these are the unknowns, and these are the observation. We want to estimate this incremental displacement. And this is the design matrix that describes the relation between the observation and the unknown parameter. This is a 0-1 matrix, actually. So this set of equations can easily be solved using a least square inversion or SVD inversion without any problem, right? So the problem is when we have some gaps in the time series. If you have some gaps in time series, for example, this could be acquisition gap, or it could be a snow cover in some point in time, or it could be decorrelation due to vegetation and so on, then it is very likely to have some gaps in the time series for some pixels. Then if you have some gaps for time series, such as this one, then still the SVD is able to estimate these values of the incremental displacements in the gap, but the values would be all 0 if you use SVD, right? SVD cannot produce a good estimation. So this is the result of the SVD estimation. So all the estimated values in the period of gap will be 0 if you apply SVD for the inversion. So LSPAS proposes a new approach to solve this issue. And so what LSPAS does is it introduces some constraints, some temporal constraints into the equation. So these are the set of the temporal constraints that are added to this small equation. And the basic idea behind this constraint is that the velocity, the displacements are linear in the period of gap. So if you have a gap, it tries to obtain the velocity before the gap, after the gap, and it assumes that the velocities or the displacements are linearly changing in the period of the gap. This is the main assumption behind the LSPAS using this set of equations. So after using LSPAS, after solving for this equation, then you will be able to see that the estimated incremental displacements are closer to reality, right? So this is the main assumption, and that's why LSPAS tries to use this type of inversion. And then after the inversion, we have one step for calculating the standard deviation of the velocities, and also one step for masking the time series. The masking the time series is a very important step because, you know, the estimated velocities and time series that we have in LiCSBAS are for all the pixels. We estimate the velocities for all the pixels, but not all of them are reliable. So in this step, we are trying to use some indices to remove the unreliable pixel using a defined mask. So mask can be obtained using a number of indices that you will see in the hands-on practical. And I just want to show an example of the masking. This is a velocity before masking. You can see there are some noisy points available in this masking due to several number of reasons. And after using the mask, this is the cleaner velocity which is produced, and the remaining pixels are more reliable. So it is highly suggested to remove the back pixels using the mask that is defined in this step. And then finally, in the last step, we have the filtering. And before going that, these are the number of noise indices that are used in LiCSBAS. Actually, I don't want to go through each of these steps, but I mean, if you just have a look at the paper and also in the hands-on practical, you can see that what each of these noise indices mean. And these are the visual representation of these indices to create this mask. This mask is a 0-1 mask, which is a combination of all these indices. And in the last step, we have filtering. And so the main goal for the filtering, but even after removing all those bad interferograms, there are some noise, some remaining noise in the last step after the inversion. So the main objective of this filtering is to apply a special temporal filtering in the time series to reduce the noise. So we believe that the remaining noise are especially correlated, but temporally uncorrelated. And this is the characteristic of the remaining noise. So for such a noise, we apply a low-pass filtering in space and a high-pass filtering in time to get rid of or to reduce this noise in the end. So this is the main objective for applying this special temporal filtering. And in the end, velocities, we provide the time series displacements and the velocities in both filtered and unfiltered, and we can make a comparison. Okay, I will leave it here and pass it to Milan to start the hands-on practical. And yeah, before that, if you have any questions regarding this big picture and overview, please.
Before the questions, I would like to apologize myself for coming late today, for causing technical difficulties for the online participants. And as most of the things, yes, you can wait a little bit.
Yeah, sure.
As most of the things regarding LiCSBAS will be kind of reiterated during the practicals, and the recording is existing thanks to Pedro. The online participants really will not miss the information stated. Still, if that's okay for everyone, if Yasser could just show the first slides before getting into LiCSBAS.
Yeah.
Yeah.
No problem.
Apologies again for that.
Yeah, so for the online people who missed the first slides, in the beginning, I just had an overview of the LiCSAR data, the COMET LiCSAR data that we have in the portal, and introduced that for each frame, we generate different interferograms, and the GeoTIFF files, which include the coherence image, and the wrapped and unwrapped data are available for each interferogram, as you see here. And also, we generate the east, north, and up components of the unit vector for each pixel. And also, we produce the multi-look intensity as well as the GACOS GeoTIFFs for each epoch. And most recently, we started to generate the ionospheric correction and the solid earth correction, which are some necessary step if you are aiming at generating a millimetric accuracy velocities in the end. And also after that, I started a brief overview of the LiCSBAS package. I mentioned that there are two parts in the LiCSBAS. One part is for the data preparation step, as you see on the left, and we have another part for the time series analysis. For the data preparation, I mentioned that we have 5 steps, which include the downloading and converting and downsampling of the data to post-read correction application, and finally masking and clipping. And for the time series analysis, I mentioned that we have 6 steps, 2 steps for quality check, and 1 step for a small baseline inversion, And then we calculate the standard deviation velocities. And then we have one step for masking and finally filtering. Then I just showed some examples for each step, starting with the download, how this script can be used by introducing the frame ID and the start and end of the time series for downloading of the data from the photo. And I mentioned that the JOTI files, the coherence image, as well as the unwrapped data are the main data that are downloaded per interprogram. And then we introduced the conversion and downsampling, and this step tries to convert the data to the floating point format, which is needed in LiCSBAS. And then I suggested to use a downsampling factor of something like 10. If this is a large area or this is your first time that you are processing this, a step to reduce the computational cost for that frame. And then the next step was Yakos correction. And this step, as also showed yesterday by Chen Yu, it will be very effective to reduce the effect of the tropospheric correction for different frames. I showed some examples. These are actually something that LiCSBAS generates, and you can check after the Yakos correction to ensure the effectiveness of the Yakos correction in your case study. Then we talked about the masking and clipping, and I mentioned that clipping is specifically something very useful if you want to focus on a small region such as a subsiding region or a small volcano or whatever. So if you reduce again your computational cost, you don't need to go through a whole frame. You can just process that specific area. So after the data preparation, I mentioned that the next steps are the time series analysis, and the first step was the quality check. And the quality check is based on the coherence, the average coherence, and the percentage of the unwrapped data. So we just apply some thresholds over these two parameters to discard the bad interprograms. And I showed some examples of the bad interprograms that can be identified with LiCSBAS in this step, and they should be removed. They must be removed, let's say, because if they still remain, they will have some negative impact in the SPAS inversion. So I highly suggest to somehow identify and remove them. Then the next step is responsible for finding the unwrapping errors using the loop closure test. And as I said, the loop closure, which can be obtained by 3 epochs and estimated using this equation on this plot, the value is 0 if you don't have any unwrapping. But in case of the unwrapping error, the value of the loop closure would be a multiplier of 2 pi. And this is the idea that we try to use to identify the unwrapping errors. And I showed an example of the unwrapping errors. The loop closure is the one in the bottom right, and the gray area was all 0, and the brown area are the areas which are affected by the loop closure, by the unwrapping error, sorry. And so using this, you can identify the unwrapping. This was another example that you can see that there are some big unwrapping errors in the loop closures, and one of the interprogram was responsible for this loop closure error. And so using a number of loops, then you are able to find the problematic interprogram and discard it from further processing. And there are some developments in COMET. I'm sure that Milan will explain that we are able to apply this kind of correction on a pixel base instead of removing the whole interprograms. Maybe it's better just to nullify those pixels which are affected by the unwrapping error instead of removing the whole interprogram. These are something that are further developed in COMET. And this was an example of the loop closure without any unwrapping error. And then we have the inversion. I just mentioned the difference between the traditional SPAS inversion, which would be problematic if we have some gap in the time series, and even using SVD approach, and then mention that LiCSBAS employs an NSPAS conversion, which includes some constraints in the system of equation, which will be able to do the estimation, and finally it was the masking and the filtering of the time source.
Thank you very much, Yasser. Thank you very much for the recapitulation. And so we will now start with the practical, where as I mentioned, we will reiterate some of the information. Just give us please some minute just to change the laptops, and maybe it will be less than 1 minute. Yeah, I'll just move it here. Okay. Thanks. Oh, yeah, actually now it's perfect time. Sorry for that. Yes, please. If that for sure there are questions. Sorry for that too. Yeah.
Yeah, I have a few questions. The question is about the architecture of this script.
Yeah.
How efficient are they? Because I
Yeah.
don't see any arguments related to number of cores.
This is
Being run on parallel for data specification.
Yeah. There are some files actually available to the scripts, which will only give the Jupyter record, and they are very efficient and they are very
This value of 1.5 means in your example, because it is not a full number.
It is for the RMS of the loops for the whole frame. So it is the RMS value of the loop closures for the whole frame. So it is, if it is less than that value, then it is okay. But if it is higher than that value, it means that there are many pixels. So this value will govern the number of unwrappers. So we don't want to remove one entire program with a small number of unwrappers. So that's why we put something like 3, 4, 5, depending on the region to identify the unwrapper.
Okay, and my last question is about this baseline network. The image or graph you showed actually is quite nice. They are very well connected to each other. But in general, there are some epochs where interprogram or each epoch is maybe connected to only one. Like if I show you like this, so we see this is the cluster, this is totally isolated, this is only connected to one. So how do we automatically explore these interfaces?
Actually, I suggest that in real cases to avoid such a network. And because in most of the frames you are produce a very dense network. But if you have some networks that is the first, you can ask us to further densify the network for you to have a better processing. Because if you just go with a very sparse network, then the estimated velocities wouldn't be that reliable. So it is better to go with a not very sparse network for the fast inversion.
guys, this seems to be a one-to-one communication. Maybe we can leave it for later.
Question is
Thank you. Right. So I need to have some breathing a little bit. Okay. We now have to split a little bit between the in-person participants and the online participants that will use slightly different way to connect to the basically computing facility. So in-person participants, here you can see the link that you should be using. I am not sharing the screen at this moment. There probably will be some questions more about that. This is on purpose because I don't want online participants to use that one. So if you can get into this web page, and you will connect as username that looks like that. I'll put it up. Yeah. So this will be username with X being a number. So I will now give you number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Will you join?
Yeah.
If you will, 17, 18, clearly. Yeah. 19. Yeah, you're too far there, but okay. So of course, sorry, there should be 2. Yeah, X. Yeah, so yeah, that's the username. The password is the same.
So without zero.
Yeah, if you no, so if you're number 3, so yours will be 03, and 10 will be just without zeros on workshop 10.
Yeah.
If you cannot connect, just raise your hand.
So the password?
Password is the same. Yeah. Yeah.
I started on the first side, no.
It will be the second one.
The third one.
The third one. Something like this after then.
Yeah.
I can't get on it.
Can I see how to connect?
Yeah.
Yeah.
So I am doing exactly this workshops.
So then when I set up here,
No, this is not working.
Yeah, but-
Here.
that's what it was, so. I'm not sure what to do.
I'm also not sure, but I was trying, and I believe that several other people did as well. And
Okay.
it was okay. Yeah, same story. It's, and you need to get the credentials, which are, we have the paper this summer, and it can link to. Okay. Yeah, so now for the online participants, I will share the link now. So for online participants, I'm sharing the link in the chat. Okay. Now I can now I will hide this slide, but if something others can help, right, for you to Pedro, can you try to help connecting as it seems not working, or maybe you can, is it possible for you to borrow the laptop or something?
You might have to.
Yeah, okay, no problem. Yeah, I remember. Yeah, sorry. Okay, so I will now share the screen and we'll get into it normally. Things were tested anyway, so this will work. Yeah, okay. So I'll stop sharing again. Good. Okay. Okay. Fine. So let me start by let's say an addition to the I'll move it like this. The addition to the introduction. So we will still not really work at this moment, as I wanted to mention basically about updates. So traditionally we do new release by every annual meeting. Every annual InSAR workshop, which is now. So I did a release yesterday evening of our version of LiCSBAS. So while LiCSBAS was developed here at COMET, this was done by Dr. Yumo Rishita, that prepared amazingly clear code that was not that easy to modify, as in the first years it seems it's a perfect tool. So we did basically just some small updates here and there, basically a maintenance and so on, and we decided to do it on our own GitHub account. Therefore, although we fork on GitHub, if you're familiar with GitHub, we fork from the original Yumo Rishita's LiCSBAS version and further develop it basically under development branch. So whenever you will feel like you miss some, or if you will like using LiCSBAS and you will miss some current development, you can always check out the dev branch to get the latest, maybe sometimes unstable codes. The codes get stabilized. Once they get stabilized, we merge them back to the main branch, which is the default. And and after like around the time of the InSAR workshop, this main branch will become the source of the release. So we now have the third release of LiCSBAS. So it basically reflects the last year of development since the previous release, and you can refer to that one. For example, if you are processing some data with this release, you may just link this one, because that's the archived one you want to refer to, or towards reproducibility of your results. If you want to show what did you really use, you can refer to the releases. This is archived one. Okay, so as mentioned, this release or the functionality was only partly described in an article where you can read about that. It's a very brief description of what happens here, but it primarily consists of a couple of things. There is a full list of what's changed, and I really would like to express the gratitude to the members of the COMET, being it our PhD student Jack McGrath, or our postdocs Chiu, or Lin Shen and Pedro as well.
Easier to use.
Yeah, okay.
Make your computer easier to use.
Cool. Sorry. So there are a couple of things that were not described in the form of article, but it's an ongoing process, like what Yasser mentioned about the notification, which overcomes possible issues with erroneously unwrapped data, further improved into solving for the reference point unwrapping error That was the work by Rin Shen. You can expect some articles soon. And we use only a couple of scripts that Chio developed, as she has also an article where she described also the other scripts that she did, and she refers to it as LiCSBAS Plus. So you can find also her scripts in the repository. We only don't really use it within the workflow. So I will skip that. But if you read the article, you can experiment with those. I would like to mention that we try to keep an eye on the issues. So whenever you will see any bug or some good idea for us to develop, or if you have your own contribution, for example, please write an issue. I would like, yeah, I think that our version is currently the most developed version. There were some updates by Morishita lately, which we are still in contact with, but less than before. And he developed LiCSBAS 2, which basically differs by adding DM error estimation. Well, error, it's basically height estimation that is above the DM, basically. So we imported that function to this repository, so you are not losing it. And also he developed a patch for downloading of ALOS interferograms that his institute is generating, like we generate in LiCSAR, we generate Sentinel-1 interferograms. He generates ALOS. I'm not sure if it's ALOS 1 or 2. I think it's ALOS 1, but okay, I'm not sure, but we added here as well. So for some areas you can also get free ALOS data. Yeah, the network is much sparser due to the acquisitions, but also not all ALOS data are available for being processed. But yeah, you can have a look on like I said, for you, Morishita, you can find also GSI maps, what is available, and you can automatically download it and process it. Okay, so yeah, so LiCSBAS. This is how our current updated workflow looks like. It's mainly the same as the original LiCSBAS that starts from the unwrapped geotips and unwrapped interferogram geotips and coherence geotips, plus optionally GACOS. And yeah, by stating that, I would like to mention that this is quite universal. So you can generate the geotips from any other software than we provide via LiCSAR. So if you have I don't know ICE 2, for example, to generate geotips, just put it to the directory that in the structure that is expected. So I recommend just trying once running within the LiCSAR, so you see the directory structure, and then just use the same for your own interferograms, and you can just run the time series or with your data. I did it a few times. It's working well. So yeah. Then the update here. Well, I would like to say that it's kind of major update here. This took probably the longest time to develop here, but you can also start directly from phase, and there is optional package within LiCSBAS that allows you to unwrap your data, where you have some you have some possibility to fine tune also parameters for the unwrapping regarding identification of noise areas, and also when you are okay with multi-looking, which means you don't really search for something very localized. This unwrapping procedure improves the signal to noise ratio basically, and can unwrap better than in our standard unwrapped data basically. So there are a couple of things that you can fine tune with the unwrapper tool. I will briefly mention about it, but we will not do it within this tutorial here. So this is just to mention that after you will get familiarize yourselves with the base, which is or the advanced functionality of LiCSBAS, you can experiment a little further to further improve your data set. Yeah. So there is what is further added is the script from the LiCSBAS Plus, which is smarter selection of the reference point or reference area, which we include in the standard processing chain. By standard processing chain, I primarily mean a script called batch LiCSBAS sh, which means whatever you will do step by step, you can automatize by setting the parameters to this script and then just run this script, including download. So basically, this can be fully automatized, or it is fully automatized processing chain. Okay. What else? Yeah. Okay. So here is the optional unwrapping procedure that I mentioned. All the other functionalities are actually included within the other boxes. Yeah. So if you will want to start from the phase data, not the unwrap, which you can again automatically download from LiCSAR, which I will show. You can basically skip or this unwrapper procedure actually does also the downsampling, GACOs, and clipping, so it basically replaces that for boxes. So yeah, but we will go through the traditional boxes, starting from the unwrap data. Okay. I think we should start, as we have already half hour delay. So okay. So for the in-person participants, this is what you should see. Can you raise your hand if there is still some issue and you don't get logged? Yeah. Okay. Is it working? Okay. Yeah. Great. Happy to hear that. So please open the folder COMET InSAR Workshop, and you will see in day 2 you will see 2 presentations. One is LiCSBAS, second is LiCSBAS stable. We will just work with the LiCSBAS that is the updated release. So I would like you to open that directory, and you will see only one Jupyter notebook here. So yeah, so please open that one, and you will work with this. For the online participants, there is an important note. So what I shared for you to the chat is a link that you can find directly from our GitHub web page. This link will always be here. So anytime in future you can just run it and follow it again. It will not disappear. On the other hand, it will be most probably updated for some visualization, also with some notes, comments that deserve updating. This link is setting you to, or will run through my binder service, which which is this one, which is not sure if people know about that. So I would like to mention with the thanks also to this group of developers that allow GitHub pages, which are just codes, to become live. Basically, this creates a virtual machine in a cloud. So you basically only add your GitHub repository and launch, and it will compile virtual machine for you, and you can return to it anytime in the future. There is one disadvantage that is basically due to the economic issues since the last year, I think, and that means the whole binder is now limited. They have only 100 concurrent users, or they can allow only 100 computer nodes. Or, yeah, so it's possible that some of the online participants will not be able to connect. If this happens, try to refresh the page. It might help. If not, then please just follow us virtually, and you will you can try touching the Jupyter notebook later on after the workshop will end. So for the in-person participants, there will not be such problem. Okay, so in front of you, you should see the Jupyter notebook. You can, if you are not familiar with Jupyter notebooks, so that's basically a Python in nice form, combined with Markdown. So every part that you click on is basically some cell. So if you double click on a cell, you can edit it, and you can set if this is a Markdown, which is a text, or it is a code. And in any case, you can click on play, like to run this cell, or just use Shift or Control Enter, and that will run the cell. In this case, it just runs the formatting. The other cells that are full of code, that will actually run the code. So please click on the first cell. The first cell is just certain things that should go quite fast. So please run this first cell by click and play, or pressing Shift Enter, or pressing Control Enter. Yeah. In the meantime, I will only do one little improvement.
The file's not there. The path still exists.
Yeah,
Sorry, what?
the file's not there, so it runs to extract data, but the something is it updated, it's going on. Is that? No, it's not there.
It's not there. It's not there. Okay, it's not there. Okay, just a second more. Yeah, just a second more. It will be there. Will be here. Yes, that's what happened. This will be fast. Oh.
It worked for me.
Oh yeah. Okay. Okay, try again.
So it's looking for this file.
If you try it again, it should be this time.
Yeah.
So sorry for that. It will, yeah. Yeah, okay. If you have run that cell, it will basically create the directory, and then it will extract only if there is not such directory. It's a good exercise also. So for the online participants, please just comment this one, and or okay, maybe easier, just write something here like this, and try it. Yeah, now it will run and extract things. So um is it working? Good. Thank you. Sorry for the online participants. I cannot check, but it should be without this issue. Is it?
I sent you the link, but I think that the problem is that the connection of the server of the number of people in there.
Yeah,
Is the online.
yeah, exactly. That's we cannot do anything with that if the online participants cannot really access it with Binder. That's really unfortunate, and that's because of many years of development. Nobody was really given funds to the Binder. So if you have appropriate institute would like to support something good, then just check about the MyBinder. They are calling for help. Yeah. So at this moment we are limited. They are limited by this 100 participants only. Try to refresh. Maybe it will work again.
If you clear the outputs on it again, that went away from me. If you like restart going on into the output, it's not working for me. Yeah, can you do it quick?
Break signal. Yeah. Okay, I see it too. But that shouldn't be a problem, is it?
I mean, it says it's done.
It says it's gone up the error there.
But it says it's done after that, like,
Yeah.
for you.
It didn't
Oh.
rerun.
So yeah,
It just says break after.
my break signal was regarding the fact that I already had the directory there. So maybe you see the same. So it's already extracted in under your username. That's possible. I hope that this is the case. Ah,
Thank you.
yeah. Okay, let's just continue further a little bit. It's possible that we lose some people on the way. If this happens, maybe it's easier just to observe, see, and yeah.
The online people have the same problem like here. When you see they missing the file of tutorial.c in the Blender also.
Seriously.
Yeah, this is the QEM.
Okay. Okay.
Yeah.
But the online participants shouldn't have this issue really. Okay. Yeah. Okay. Okay. Oh, so okay, for online participants, I believe there is one thing that that it would work anyway, because that data are most probably already extracted there using using the post build. So yeah, okay. That and it was already extracted for you. So if you see such a message, I believe you can just ignore it, because it should be working. It extracted it, and you should be able to get to the directory. So yeah, sorry for any erroneous message, but that should work for you further. Yeah. Okay. So The tutorial will be very similar from like as the previous year tutorial, and you will see the recording as well, so you can always get back to it. And yeah, please inform us if you really cannot proceed a little later, so we know we have some bug and we should correct that one. Anyway, we will be looking to the time series over the over Campiflegrei volcano caldera that is situated close to the Napoli in Italy, and close to Vesuvio, which is here. You probably know about the famous eruption and archaeological finding next to it. Yeah, and Campiflegrei is currently actively inflating. Actually, there were some tremors this year that quite shocked the local population, but fortunately nothing is happening at this moment. So this figure shows what the GPS actually measurements are showing over this area, accommodated in the agglomeration of around 15 million people. There is incline of the, yeah, basically Daikin magma, right? Am I correct? Well, and we can have a look if we will see such signals also from InSAR, which we know that we do. But yeah. So first of all, if you are interested in some event like this, you would like to check and process the data, you can do it yourself. We generate interferograms and share them within the COMET LiCS portal. So basically, what you can do, you can check if you have your area of interest covered on the portal. You see the black boxes means most of the data are processed basically, and you can find the area of interest. You can find you see we have a couple of frames that are almost fully processed here, from the sending pass as well. Some weird ones as well, but there are also some good ones. I think we are using this particular frame 022D, maybe slightly different ID, but anyway, okay, yeah, still that strange network. But basically, what you can do is just to copy the frame ID, and that's it. Then you start from here. Here in this tutorial, you don't have to do it, as we pre-prepared the data. Otherwise, you would need first to download the data and so on. Sorry. So once you have your frame ID, in the first step, you should get the data from that frame. So you can use LiCSBAS 01 get geotiff, Control Enter, and yeah, there's some warning. Please ignore that. But you will see help. That's how the Jupyter notebook is set, basically, that you can just run the command. You don't have to edit anything. So the help files, or the help of the scripts, will tell you exactly what it does, what you can set, what will be the output files after the end of the procedure. And in this case, it will just get geotiffs, the unwrapped interferograms and coherence for the frame ID from LiCSAR. You can set the start date, end date. You can optionally get GACOS data, so you can apply the correction, or you can get some other things. For example, if you will want to do the re-unwrapping procedure, you can just get phase, and that will download also directly the phase data, not only the unwrapped data. There is the option to set minimum and maximum temporal baseline because we sometimes generate too long interferograms that mean much more data to download if you don't actually need it. So, and on the other hand, minimum can be useful if you don't want 6 days interferograms that show strong phase bias, basically. Yeah. So that's the first step, and you would just download the data, and the procedure will set the directories that will be then used for the next steps. So I'll skip that one because we have pre-prepared data. Now let's get to the other cell, and again, Control Enter. It will show you help for the other that is also pre-processed, so we will skip it. And this cell will basically do the multi-looking on the unwrapped data. As I mentioned before, you can actually benefit from multi-looking and unwrapping. Here you can get some information. If there will be time, I will return to that. Yeah, you have the option. So here, when we only multi-look or downsample, basically, the unwrapped data, that's yeah, primarily for faster processing. And what is the usage? Well, here you have to. This is the mandatory parameter. The other ones are optional ones only. The only mandatory is to set the geog directory. What is geog directory? It's that directory that will be where the data will be automatically downloaded to. So this is the input. So after the step 1, you would get the data downloaded to the geog directory. So that will be the input here. And the output of the multi-looking, where you can choose some multi-looking factor, you can keep multi-looking factor 1. So no change will happen, but you should still run it because this script will also convert the geotiffs into the binary format. So you can use -n1. Otherwise, so our interferograms are by default in 100 meters resolution. So by multi-looking 10, you basically downsample the unwrapped data to 1 kilometer resolution. In this case, we multi-look only by factor of 2 for this practical, and that has been done already. If you had no non-Sentinel-1 data, you can also set the frequency. Here is here you see examples what you should add for data if you use ALS data or ALS2 data. Yeah, again, that's optional. By default, we are using Sentinel-1 frequency. Okay. Now, GACOS correction, that's the next step. So once we have the multi-look data, we can so unwrap data in the standard way. We would reduce the data for the GACOS correction if you have downloaded it using the get GACOS in the first step. And here is just some example that is automatically generated within LiCSBAS. So all the figures that you see, you can find also in the directories. So in this case, in the output directories, you can see these figures. So here, as an example, you see the original unwrapped data. This is the correction from the GACOS that is done by LiCSBAS, and here you see the corrected. Oh, sorry, that's the corrected. That's the corrected interferogram, and the one on the right is the model based on GACOS. So you can see actually that GACOS nicely captured these long wave features, and you can also find the overall plot, which tells you basically about the standard deviation per each interferogram before the GACOS correction on x-axis and after GACOS correction. So you can see that that before the correction, the standard deviation could have been high, like 15 radians, for example, which is very high. And after the correction, the same dot is somewhere about 6. So that's showing that the GACOs perform very well, which is not always the case because it depends on several factors, but primarily about the quality of the model that is being used. Yeah. Yeah. Okay. So I can just for completeness, I will run the help of the other command. And yeah, you can see that there is nothing to it, just what is the input directory, what is this output directory that you will use afterwards. You can name it as you wish. Yeah. Normally it's named geoc ML2, for example, if it's multi-looked by 2 GACOs. So you clearly see based on the name of the directory what has been performed. So further another optional step is the masking, which in this example we are masking only based on some region which for which we can use just the clip-in. That is the next step. But what I would like to mention is something very useful in my opinion, and that is possibility to mask based on coherence. You can mask based on average coherence, which you can do the same after the time series inversion. But sometimes what can be useful is threshold on to individual coherence, which means you are masking every interferogram based on its own coherence. So if there will be some bad coherent points that are barely unwrapped, you will definitely not add that signal to the inversion, which could basically decrease the quality of your product. So that one is very useful threshold. Yeah, still this is optional. Clipping was also mentioned. That's where you can set, for example, geographic coordinates of your clip area, and this is what we did here. Actually, this is the whole frame, and okay, maybe it's a slightly different area, but we would be cutting only one small part of it, and that's where we start from. So you don't have to process the whole frame because you don't need 250 times 250 kilometers result most probably. So the clipping is also very useful function, and you can see the parameters. You can either set the -r is just the pixel parameters, or -g is when you have longitude and latitude corners basically. You can also use polygon, but yeah, I think that script is that way is the most convenient and useful. Okay, so that's preparation. That's the module 0 basically. Yeah, 0, 1, 0, 2, and until now it's 0, 5. So so this is where we start from. That's what we prepared, and you extracted that zip file with. Is there anyone from in-person participant who got a little lost already, or maybe there is some particular question at this moment before I will get into the time series itself? Okay, fine. Thank you for that. Okay. So now let's run the time series itself. So here after this procedure, you will realize that you have actually several directories, and you don't need all of them. So there is directory geoc with the original downloaded data. Then we would multi-look. Then we would optionally add the GACOs, and then we can have geoc ML2 GACOS script, which is optionally by the clip dataset. And basically, you need only this dataset because that's ready for the time series. So let's have a look on content of our folder. So here we see, okay, we are in this folder named by the frame ID. And if we go to LS, we see that we have the situation before clipping and after clipping. Okay, in my case, I already have the time series as I was trying it here before, but you will not see that one yet. So we can explore what is inside the folders. I see there is probably a lot of questions, and my suggestion is to just follow if you got lost somewhere due to technical issues. And so so here we see that the folder geocml to Gacko script contains 886 interferograms. And here we see the last 30 folders and files. So we see that our data set will now stop in 2021. That's our aim, to process only subset. And because we use the Gacko's data, you see the PNG file that I showed before, and some other information, other things that can be sometimes useful. In most of the cases, we generate the PNGs, so you don't have to dig really deep into the text files and trying to understand what information it brings, but you can just have a look on the PNG, and it's usually clear to you what's going on. Okay, let's check the interferograms network. This will not work, I know, but still run it, please. So this command will generate PNG file of the network, and there is an issue with the name of the PNG. So I'll just find it. Yeah, it's just named differently. So I'll show it to you this way. Oh, I'm not sure why, but okay. So this would generate a network plot, so we can see what is our data set, and this is our data set. So it starts from 2016 and goes until 2021. So this is the interferometric plot that we start with. Okay, see, it's a very nicely connected network. So there are no gaps at this moment. So you will not. So you can invert basically. If we would have this network for each pixel, you would be able to invert everything with the fast SVD approach, with the like small baseline approach, basically. Okay. Yeah. Yeah. But you will get you will see the network in later stage. Actually, also I wanted just to show here what we are working with this sort of with this number of interferograms that are clipped to contain the conflict flag area. Okay, let's look into some random interferograms. So basically, I just chose one of those pairs here, and just let's have a look. So LiCSBAS would generate this sort of previews. The preview is a preview of the unwrapped data. You see, we multi-loop, so really the 200 meters resolution is not really much, but that's enough for our processing at this moment. You can see that the color scale is actually 6 pi per cycle. So indeed, it's unwrapped, but it's basically rewrapped back only for the preview. Yeah, so it might be a little bit misleading, but at least for the idea of how the interferograms look like, here is one. This is 12 days interferogram, so the coherence was very low. So you see there is only one pixel with low coherence that was masked already during the unwrapping process. And I believe that this one is some erroneous, for example, right? Could be. The color is not really, or there is some noise around, maybe some vegetation or whatever that doesn't keep the consistency of the long wave signal. Simply some high frequency signal is can be found. Okay. And we have 885 more such interferograms. What's that? In this cell, I wanted to show the preview that is generated when before clipping. So you remember the GACOS step was performed before clipping. You can actually freely operate with these optional steps. You can first clip and then apply GACOS, but okay, in this case I did it this way. So so here is just an example to show you one of the PNG files where again here we have the original interferogram. This is the model from GACOS, which again very nicely corresponds to the long wave signals that is getting removed, and you can see that the standard deviation actually dropped from 5 radians to 3 radians. So GACOS helped very much here. Okay, let's see the effect of GACOS version 2, which is you can actually have a look also to the GACOS info files. So also the text files make sense. And when else will you have a look at those text files than during the tutorial like this, right? We usually skip looking at that, but this is very informative because you can see information for all the interferogram, where you can see that this improved by 36%, for example, the other by 30, and so on. But there are some cases where GACOS actually increases the standard deviation. It can happen. Yeah. Okay. And now finally we can go into the basic time series analysis. So in the first step, as was mentioned, so the module 1 means time series processing. What is a 0 is actually playing with the interferograms themselves, and starting from 1 we already do the time series. So first of all, we are checking the algraph data. That's about the data consistency, where they barely stored, downloaded, maybe, or there are of some low quality. For example, very small portion of the data was unwrapped due to generally low coherence, and so on. So there is also an option to remove, plug and remove the interferograms that have too strong ramp, which is happening in the data, let's say, before the middle or before 2016, when there was strong solar activity. You could see strong ionospheric ramp that we currently have ways how to avoid or improve, but we still have the old interferograms generated some time ago with the older approach, and we still have some interferograms with strong ramp in 2014 or 15. So it's possible to remove them by a parameter. So here you can see some parameters. There is a coherence threshold, which, by the way, this is I think important to mention. Here we basically drop interferograms from the processing, right? So we say if the average coherence of given interferogram is okay, in this case the default is very low number, but let's say you want to mask everything what is in average below 0.3 or 4, you want only good interferograms, then, which is sometimes not the best idea because you will get gaps, but okay, you can do it. Those parameters would remove that particular interferogram from the processing. Yeah, that strong ramp that I mentioned, that's the -S here. Yeah, that's the co-registration error in the form of significant azimuthal ramp. Yeah, so let's just run it with the default parameters. default parameters are always stated here in the help. So the default, if you don't provide it, as you see, all of those bracketed ones are in as a optional parameters. So it will drop down to defaults. So we use coherence threshold of almost 0 and coverage of 30%. So at least 30% of the whole image must be unwrapped. Yeah, otherwise it gets dropped. So what is the status here? With this, we are discovering 30 interferograms. This is their list. This is their statistics. So you see their unwrapped coverage is very low. Almost nothing was unwrapped here. And the average coherence was also very bad. Why is this here? It's might be due to missing bursts, which is also some issue we have to deal with. But very often it is because of a long interferogram. But in this case, it's most probably just this area was not processed like we had probably only some portion of the burst that was processed there. Yeah, that's it. So we are dropping it. Okay, now let's have a look on the TS directory that is generated. So by default, we keep the same folder name, but add just TS like time series before that. And you can see that okay, you will see different outputs because I already was running it, but you will see 11 folder 11 RAS and so on, and inside that folders you can actually see linked PNG files, so you can also manually have a look what actually was removed and why. So or you can see it in the text version again for all the interferograms. And here I will show you one of the discarded interferograms. And okay, so this is what I mentioned. Yeah. So okay, I didn't mention that. But so this is not about the non-existent burst. There is another issue. No idea why. But we have only that couple of pixels that are unwrapped. So of course we are dropping this interferogram. That doesn't make sense, right? Okay. Now we can see. So again, everything is generated here by LiCSBAS. So you can have a look on the updated network plot, and after the step 11, you see the red lines. That's what we are dropping. That's the 30 interferograms that we drop. Time is okay. Good. Right. Any question at this moment? Okay. Now that was the basic check. Now the second check is about the loop closure. So again, it was mentioned, but it's always good to repeat things, especially when you see things for the first time, right? It can be a little bit confusing. So indeed, there is something called loop closure test, which basically say that if we have a triplet of interferograms, so you see that this is epoch 1, 12, December 2017, 3rd December, connects with 15th of December. Then we have the same 15th of December connects with the post Christmas time, and then we connect the first epoch with the last epoch. So we basically have the triplet here. Yeah, you can see it mathematically here: 1, 2, 2, 3, minus 1, 3, and the result should be 0. If it's 0, means the unwrapping is consistent in all of those 3 interferograms. That happens actually independently. So it's reasonable to think that the unwrapping is correct if the loop closure is 0. In this particular case, we have area here within the loop phase that is not 0, and that's an issue. And that will, if we will keep it like this, that area will basically jump in the time series, right? Or of course, well, the quality will depend on the other interferograms, because we have strong redundancy. So you can see between each epoch. Okay, let's find some. It's not really visible, but let's say that we want to invert the increment between where was that, 2017 December. Yeah, so there is there are some two epochs in between. We want to get the increment, so basically the difference between the epoch 2 minus epoch 1, and that in between that epochs we have not only that one connection, which can be wrong due to unwrapping errors, but we have several others that cover that time period. So basically, all the interferograms that cover that period will be used to invert for that increment that we then can sum into the time series. So if we have only one one interferogram, and that will be wrongly unwrapped, that error will be shown in the time series. But if we have many, that one bad will actually cause an outlier. So it will decrease the quality. It will increase RMS of the residuals here. And yeah, so we have some measures how to be careful about that particular areas. We can also fix it. So by the first fix, well, what we can do here in the step 12, which is the standard version of LiCSBAS, we can just drop interferograms that create that bad loop phase, let's say. But then we are losing the interferograms, right? Then we are losing the good areas here if we would drop that, right? That affects only this small area that maybe is not that much of our interest. We can do the removal of or identification of which of those 3 unwrapped interferograms is wrong, and we would nullify the pixels only. So we are not losing the information. So that's an option, a very good option in my opinion. Within I'll implement it as the nullification. Okay, here I write some details if you will want to read more about that, but I will show you first of all just the help. Yeah, so because I think that point deserves some discussion about that, because that's quite significantly improving the data. So here we can just set the path to the GeoCamel directory as usual, and here we have the threshold of RMS of loop phase. By default, this is 1.5 radians. What does it mean? It means that if the triplet will be in average higher than this threshold, so I will return back to the picture. Here you can see that the average RMS here is 2.26 radians, right? So this is above the threshold, and here if we will keep it below the threshold, we are basically removing that interferograms from processing. So that's one option. Second option is to use the nullification per pixel, which has also some negative aspects, but still I think it's useful to use it. But the nullification will be performed only on the interferograms that you don't drop by this threshold. So in my case, for example, what I usually do is I set this threshold high. It depends on your data, but you can use 10 radians, why not? Because you will then nullify per pixel. So I would normally do minus L10 as I mentioned, and nullify, and that's it. So that's what I wanted to mention. Let's try it here. Let's keep it with the low. So okay, another thing, the nullification can take some time. That's why we'll skip it here now. But let's just run the command as it is stated here. So let's only remove the interferograms with that cause the loop closure higher in average than 1.5 radians. So there is first step, second step, third step that is explained just above. Fourth step, generating the PNG previews and error. That's wonderful. Okay, that's wonderful. Yeah. Do you see also this error?
Yeah.
Yeah.
Oh gosh. Okay. Yeah, I think it anyway could have worked. So let's just skip the PNG generation, which I will do by no PNG. So we will skip the PNGs, but yeah, at least to see the result. Okay. Yeah. Okay. Now it generates the average coherence, number of unwrapped data, and loop errors, and some other things. So we can have a look what happens in the text file. So here we see some information about what was removed, what was not removed. In our case, we have good data set, so probably nothing was removed, even with this very strict loop threshold, which is nice. Now let's have a look. Yeah, there is absolutely no bad loop PNG, and as I mentioned, this is very strict threshold, 1.5 radians in average. So that means the data were wrapped very well in this particular case. Okay, so I will skip the other cell because we don't have anything.
Excuse me.
Yeah.
Threshold 1.5. I think it how why is it 1.5?
How
How you define the threshold 1.5?
like how I got into that number?
Yeah.
Yeah. Basically by experience, but so we work with the radians, right? So yeah. Yeah, maybe if it would be already in millimeters, it would be more intuitive, I think. Yeah, but we have it within radians. So what does it mean? So 2 pi, one cycle would lead to half of the wavelength of deformation. So that's in this case is 2.5 centimeters. For 2 pi, that's say 6 radians. 2 pi. So yeah, you can calculate how much it is in millimeters basically. Yeah, it depends on amount of pixels that you have in the input, right? Because we are speaking about the average, so I cannot just give proper number what will be the best, because this depends on your area. I think it makes sense to just try and take a look on the PNGs. For example, okay, I'll give it a try and we'll set it to something ridiculously low. Oh, sorry. Okay, maybe even lower. Okay, I'll just 0.6. This should drop something. Yeah. After running, you will see the information in text file. So here you can see that that some RMSE was 0.6 without like before adding the reference point. With adding the reference point, it actually got worse a little bit. So yeah, but I didn't generate the PNGs. Yeah. Okay. So there is some issue. I hope this issue might be only here. Some maybe we didn't install SCM properly. Yeah, so I cannot show you now the loop PNG, but basically it's the same picture as here. You would see basically these pictures for those loops that were identified. So you can understand what's going on and if you are happy with that or not. For example, if you're not interested in this particular area, you can, for example, keep those loops and have the processing further. Yeah. You don't have to be too strict here, at least not at the beginning. It makes sense to try first just with default parameters and then just fine tune accordingly, according to the situation. Anyway, I dropped some. So after running, you will see in the TS geog directory, which okay, I can show it to you, that you will see new information, new folders that are related to the step 12. So you will see the bad interferograms and their PNG files. You will see some information in the loop directory, including the reference point that was the preliminary reference point. And in the folder network, you will see this figure. So you will see network 11, like after step 11, how it changed. So if we would be too strict and it would remove most of the interference and everything would be in red, that's most probably you will see that you don't want to work further with such data sets. So you will have to update the thresholds. What you want to have is a really connected network without gaps, preferentially. And with such network, you can do the small baseline inversion. Okay, is there any question at this moment? That was already a little more specific, let's say, to the time series analysis.
Just
Yeah.
to make sure, for example, for many of the study areas when there are a lot of ice and glaciers, for example,
yeah,
when
okay.
you have like a winter
Mhm.
dominant, so we have to exclude these images already from the beginning, right? So you already have the gap in the network. Does this prompt us somehow reconnect these gaps?
Yeah,
How
so
does it work?
okay, that's so indeed, the quality of the time series will depend on the quality of your network and the interferograms. If there are glaciers during the snow period, it will most probably cause decorrelation, therefore like lower coherence in general with related unwrapping errors. Or nothing much will be unwrapped at all, depending on the way of unwrapping has been done. That's why it's good to experiment also with this optional 0 to 205 unwrap. Still, most probably, if you connect the interferograms that contain that physical information of snow, that may actually be unwrapped. Okay, most probably not, but in some cases it might. But still, what do you measure? Right? You might measure just the snow, right? So what you probably will need to do is make sure that you have interferogram connecting the situation before and after winter. Yeah, which will be long time period interferogram, so it might be also pretty much decorrelated. Yeah, that's an issue. That's an issue. So you can try densify the generated interferograms, the network, like trying to, because just directly after snow melts, there is very often low vegetation. So you may be lucky and get relatively good coherence. So the unwrapping will be possible. With the multi-looking before unwrapping, you can get better result as you basically gather more distributed scatterer into one cell. So if they are oriented, if they induce more or less the same phase due to the deformation, that signal might overcome the noise signal of phase due to vegetation or whatever. Yeah, so So yeah, but if you have the standard network like in this case, where we have basically up to, let's say, 60 days interferogram, you will probably identify issues and in using the loop errors, and then it's best to not use those interferograms, or at least use the nullification. And you will basically create a gap. That's true. The gap will be estimated under assumption that there is a linear velocity trend. So that might be correct, maybe not. That's so regarding the gap filling, there is actually slightly modified option. Not very well described, but that's the singular approach. In the first place, it's good to keep the core LiCSBAS NSBAS inversion. But sometimes when you will, especially when you will see the, let's say, connected clusters that are being strangely shifted due to the gap estimated as it was, and you would see some nonlinear motion. Actually, it's this singular way will actually estimate that gap slightly differently by not fitting the whole clusters into one line of the trend, but only connecting the basically last epoch with from the first cluster and the first epoch of the other cluster. So the clusters might shift into something that look more reasonable. That sometimes happens, especially when the gap is small. If you have a long gap, you cannot simply trust it, I believe. Yeah, it's that's, yeah, there is a lot of tricky areas like this. Yeah, but that's the limit of INSAR, especially with C-band. Well, with snow also L-band would not do much, but with the L-band you might have good coherence also in longer time period due to the correlation in time not being so drastic as C or X-band. Yeah, that will not work due to vegetation or any other scatterers that are of similar size of the wavelength, basically. Yeah, so something like that. Okay. Yeah. Another question? No. No. Okay. So let's already see some result. So the main result is the result of the inversion, right? We want to invert the network of interferograms in the cumulative displacement. So that's what happens here during the step 13. Let's see the help first. Because you have quite a number of possibilities what you can change there or choose there. Some favorite ones. Well, you can use the inversion algorithm as standard, the least squares, and that actually can help a little bit in some more complicated situations. You can use weighted least squares. What does it mean? You're basically adding weights to that interferograms during the inversion that are based on coherence. So basically, the better coherence, the more weight it will have. So the inversion will trust more that particular interferogram than the other one. So this is what you can use. It can save some situation, but it has a rather subtle effect, I would say. And also the negative aspect is the phase bias, because if you use the 6 days interferograms, they are crazy biased very often, and but they have very high coherence, so that signal will actually overcome any other interferogram generated there. So yeah, everything has its pros and cons here. So yeah, I mentioned briefly about Singular. That is more economic computation. It simply goes faster because it's simpler calculation here. But you can also, and this is what we will try first now, skip any interpolation, any LiCSBAS inversion, and perform only SB processing with the flag only SB. So yeah, I think I will not mention the other ones. These are not that important. Yeah, I will not mention. So first of all, I will try with only SB, although I'm not sure how it will, what will happen now when we are missing the color map. But I think I have pre-generated data, so you will see it anyway. So when I will try doing only SB, we might see that not everything gets covered, but this will be good to see, good to show. So it takes a little bit of time, but the only SB is very fast inversion. You can see that estimated time would be 1 minute. With the Singular, it can take 7 minutes. If you use the standard LiCSBAS approach, it can take 25 minutes. So that's basically the main difference. Okay, so here we are done. And some simple explanation. This is outdated a little bit because it would say that the Singular actually is using that strange computation, but it was later changed into the velocity fit-in. But yeah, that doesn't matter now. Okay, we can have a look at the network because some parameters could have caused some other interferograms being dropped down. So it's always good to check the network, what we are working with, you know, like maybe by some chance, but by some too strict parameter, in this case, that was threshold for the unwrapped interferograms per pixel. We might see that actually our processing result is based on only 3 interferograms also happened. So we know that we shouldn't trust it. But here on the other cell, we already can see the velocity. So, okay, here we have our velocity map. And it looks good, actually, even that it was done with only SB. So what does it say? Like for most of the pixels, we have full network, no gaps. There are still pixels where at least one gap caused some like some non-value, something was not unwrapped in this particular pixels. So yeah, we can rerun the procedure. Yeah, by the way, don't be afraid of rerunning things in LiCSBAS. I think it's well done. So it will not. So it will. Yeah, it will just regenerate things needed. Without worries that there would be some error. You would lose something, for example, in nullification. We still keep the backup data that will automatically get used if we will reprocess the data and so on. So yeah. So now what I'm doing, you don't have to follow this time because it takes some time. Okay. See, it takes a little bit longer time. I've set it to use the Singular approach. I will not try the third one just for the time case sake. And yeah, it's quite fast now. In these computers, that 7 minutes that was we use binder, that's slower. Yeah, so 36 seconds we're done here, and we should have now interpolated the gaps also of that. Okay. Stuck here. Okay. Now it should be fully covered. Yeah, it is fully covered. So that's the difference between the SB and SBAS. Yeah, basically. Yeah. So we could fill some little gap. Sometimes there is just one gap with the assumption of the linear velocity. It might not be that bad assumption if we want to interpolate only from like 12 days period or something like this. So I shouldn't be that much worrying situation. Although there can be some approaches where you will consider non-linear motion like sinusoid, for example, but yeah, it depends on your data set. In this case, we have nice result, nice velocity, I think, and we can proceed further. So so then we would like to know how reliable this actually is, right? Like in this case, we have very nice data set. If you had less interferograms, you might get the velocity with high RMSE. Or okay, in this case, we don't speak about RMSE. We speak about the velocity standard deviation. Although this is actually RMSE, but calculated in a little different way using bootstrapping. So again, I show some help. You can just keep the standard parameters. That's fine. There's nothing much to change here. There is maybe something worth mentioning is the ransack option, which was a fast addition only. And basically, if you have outliers also after inversion, this will re-estimate the velocity, removing or not caring about that outlier. So basically, bootstrapping method applied for velocity estimation. But yeah, it works, but maybe you will not need it really. So here by this step, we are calculating the standard deviation of velocity, which you can see that in that area where things were red, we have lower accuracy basically, but not that bad because the estimate of the standard deviation is still less than 1 millimeter per year. So that's very good. But you can depict also some other areas that are more noisy, let's say. And there is another layer that is being generated, and that's spatial temporal consistency. That's basically spatial temporal variance, we can say, or yeah. Again, let's call it standard definition. So consistency in 3D, not where we basically care about each small window in space and time. So this layer is not affected by the quality or distance of the reference point. So it can be useful again. Here the reference point is playing a role. So for example, if we would have larger frame and the reference point would be much farther, you would see actually how farther you go from the reference point, that the standard deviation gets worse. Yeah. Okay. So here in the spatial temporal consistency, we see that actually this area is not that noisy. There are some other noisy areas. Probably there is some forest or something like it. Okay. So after this step, we get into the yet another set of quality measures that are being generated during the masking. So you can basically mask the noisy pixels as you see in this area. This is the velocity from the previous processing, previous version of LiCSBAS. And the unwrapped data, where we see some strange outputs along the coastline, and these areas here are also looking a little bit weird. And when you run this LiCSBAS 15, just with standard parameters first, it will generate this particular figure where you see actually that other information that you can read in the paper about LiCSBAS, for example, you can see number of gaps, for example, that is also related to the maximal time of each the cluster in between gap, let's say. So if you have 1 year of data without gap, you can trust it, for example. Yeah, if in this case the yellow cases are higher than 1.5 years. Yeah, so that's the logic in between. Here you can see also the RMSE of the residuals from the inversion, which is not the same as the standard deviation of the velocity fit in the cumulative displacement. That this one is actually saying something about the quality of your unwrapped data, because that's the RMSE of the inversion from the interferograms of the residuals there. Yeah. So that's very good layer to put your mask based on. And yeah, so here is some list of the possibilities. And if I go through the help, you can use the mask before the final filtering step based on, for example, average coherence threshold, or the number of unwrapped interference, BSTD, STC, various things. There are some new additions. For example, you can actually estimate the average phase bias and mask based on that. Yeah, or yeah, that's not needed to mention, I think. So when you run it, here I'm running it without any fine-tuned parameters. I'm just running it with the defaults, and you can see that when you run it, you'll see the list of the layers that were used for making the mask, and you can see what were the thresholds, because that's the defaults here, and how many pixels were masked. So, for example, based on a very low value of coherence, we mask 2% of data. There are more, 6% of data had at least 10 gaps, and so on. So afterwards, you can mask some of those pixels that were less reliable. So that's quite key. Very often you end up in masking 90% of the pixels with the default parameters if your network is not that good, or yeah, if you have more tricky area than in this case. So and again, if you search for the information in the TS folder, you will see new PNG file generated mask TS, which I think it's really key. Yeah, key figure in your processing. So here you see all those mask layers with, okay, now what we added is at least to know where is the reference point. And here you see the layers that were used for the masking, and everything is in yellow. Why? Because the thresholds were set too high, basically. So the colors would change if we would play around with the parameters, set some more strict masking. Let's say VSTD by default was 100 millimeters per year. So that's why we see VSTD as yellow. In fact, that just should be number around 1, for example. So yeah, you can play with that a little bit afterwards. Yeah, there's a new layer and loop error in a ratio, which basically means, here it means that 0.7 here would mean that 70% of the interferogram loops contain an error. Yeah, that's extreme. That's why everything is yellow. We are verified. But just for your information, that you can use this ratio also. That's not used by yeah, by the standard LiCSBAS version. Okay, so yeah, here we can slightly modify it, but yeah, that's not really needed. Yeah, okay. Yeah, here here I was in the other cell. I was changing the residual RMSE to 2 millimeters. So you can see that the figure now changed, and you can see it clearly. You can see it better simply. Okay, so now when you have your mask ready, and when you are happy with the basically the masked velocity as it's shown in the mask TS. You can use that data for final step, which is the filtering. And as usual, you have several options how to filter, and you can estimate and remove the ramp. What do I mean by ramp? It's visible in this figure and was shown by Yasser also before. So for example, here in before the ramp in this particular, I think this is increment already, not interferogram, but should be increment. Contains some ramp, yeah, some long wave signal, and we can get rid of it if we, if we are interested only in some local deformation, let's say. So we can estimate it, remove it. What is also very useful is removing phase that is, or phase, or incremental displacement correlated to topography. So that's a little bit tricky because sometimes you, in case of volcanoes, for example, you have really deformation that is correlated also to topography. You don't want to remove that, right? Unless you have, for example, several mountains in a belt, and only one of them is volcano, and you still have strong tropospheric variation. For example, you didn't have geckos or whatever, then it's reasonable to correlate with topography containing that several mountains. So this will get removed and your volcano would hopefully not be that much affected. But if you don't study volcanoes, like feel free to use it. You will see such figure before and after the correction. This is the, yeah, okay. And that line is the correction. So basically that correlation between the displacement and the height. So it's good to check that figure because you will basically see that the whole data set that you have might be shifted by that line. So please be careful about that. There are a couple of options. For example, you can limit the minimum and maximum height. So you don't want to take into account some low grounds that would get into that correlation, but you want to check only about the phase gradient on the higher peaks of the mountain. So there it would get estimated. Some linear trend would be estimated from only some higher height values, let's say, and then it will shift all values accordingly. So yeah, there are still things that you can tweak. That's as usual. That's like probably the best is using the external models if you have them, like geckos, yeah, or ICAMs or anything similar. If you're not happy with the HRS model being used with geckos. Okay, so there are some couple of things that you can change within the filtering. As I mentioned, there is the HGT linear. That's the DM correlated signal removal with the possibility to set minimum and maximum heights. You can set the spatial, like size of the spatial window in kilometers, temporal window in years, so 0 point something, yeah, here with minus R, that's the deramping, where yeah, you can use just the degree 1, which I think that will do the same as bilinear, basically. And what is new is also you can estimate and remove, but primarily it's estimated, so you can work with that, the DM error phase. So that's basically the DM that was, sorry, the heights that were not contained in the DM during the process of generating the interferograms. Yeah, so there are some other little things that we will not use. So let's just try it. This may take some time still. So what I'm doing here, I want to show only the result of the ramping and the AGT linear, and I said no filter. What does it mean, no filter? You can just skip the spatial temporal filter. This is not really recommended here. It's done only for due to the time, as it could take yeah, it could take the longest time. Even now it will take some time actually, because the AGT linear will take time because our data set is quite long. See, we have 283 epochs, and each of the epoch or increments will get correlated with the height. So that's why it takes time. So okay, maybe it's not the best idea now, as it takes too much time. So I will stop it now. Yeah, you can stop the process actually by in Jupyter Notebook, and I will just remove that AGT linear for now, as I know the data set it will not change much here. Yeah. Okay. So now it does only the deramping, which is again quite slow. Yeah. Any questions? Because actually, this is the last step. After this, you will have your final result already. There is a spatial. Okay, maybe just to add about the spatial temporal filter. That's actually modeling atmosphere, like residual atmosphere. So turbulent atmosphere, I can say, as we are using high pass temporal filter, low pass spatial filter to estimate the noise that is not really correlated in time, because the atmosphere is changing every time. Yeah, so there shouldn't be any correlation in time, but it's smooth in space basically. So here by default we use the spatial window 2 kilometers. That's for let's say moderate turbulence. You may want to capture also higher frequency turbulence, as sometimes it happens. So you can also try something like half kilometer, but it depends on how high resolution your data is, right? If I would put filter width size half kilometer and my input data is 200 meters, then it's perhaps not the best for the Gaussian window to go through. But if you have higher resolution, why not to set that capturing the details, let's say, that will otherwise affect the quality of your results. Okay, so yeah, still no questions?
So what is the exact relationship between this filter value and pixel size? Maybe, for example, if we are using 40 megapixel, then 200 meter filter value is recommended.
Yeah, so I would say this, if you remember Chen Yu's presentation, you have seen this overall view on the world, let's say, and some areas were really red, which means very strong atmospheric corrections were identified using GACO's data, right? That was the India case, or some other areas that were really red, and that red would mean basically, I simplify it a little bit, but it would basically mean strong atmosphere and when you have strong atmosphere, you primarily have strong turbulent atmosphere as well, right? Usually it differs between descending and ascending, also because evening time can have like locally different conditions than the morning times. And the GACO's sampling in time is not really good at this moment. ECMWF changed their model, so it might be a little better, but still it will not be sampling every 1 hour as some others. So you are interpolating a lot already in the model. So the GACOs will not capture the turbulence properly. It will capture the topographic related errors, let's say atmosphere, which we can capture with the HGT linear maybe from the data also, but that's still maybe. But the issue is primarily the turbulence. So it depends on your area, and it's normally we say that the atmosphere doesn't cause strong variation in something like 500 meters, let's say, yeah. So so if you set 2 kilometers, you are more sure that you don't remove the small displacements that happened once, for example, that are not temporally correlated, right? If you have linear velocity, you don't have to bother about that because it will not get estimated as atmosphere because it's linear, let's say, in time. But very often you can have some events, some small earthquake or whatever that can be mapped as atmosphere. So it is so the Gaussian window we use is quite smoothing things. So you would not get rid of all the signal, but yeah, you can experiment probably with maybe some shorter data set. The default parameters are set quite okay. So you're free to go with these ones, but still it's 2 kilometers. For example, sometimes you can have, sometimes if you look into the tectonics, for example, you may multi-look data times 10, and you will end up by the fact that the 2 kilometers would be just 2 pixels or 4 pixels in 2D. And the Gaussian window in that 4 pixels will actually not do anything, we can say. So yeah, or maybe opposite will remove everything. So I'm not sure now. I will need to think about it. But yeah, so yeah, but 2 kilometers are quite fine. Yeah, you are not risking that you would filter out the real deformation. Yeah, yeah, and that's like physically fine. So it's something what I wanted to mention is something about visualization. So take this one as a recommendation for a tool that is being used by the community, where you can again, it works with NetCDF easily. So you can here, if you were ever wondering how come that people have so beautiful figures in their papers, how do they do it? They use GMT or the updated PyGMT version that is for Python, and we are further developing things to be able to produce various figures using this tool. So there is a very nice Jupyter notebook, same story as here with LiCSBAS, but step by step for understanding the GMT and GMT figures, so you can create some nicer figures. Yeah, I don't have nice figures here. Maximally, I can show this example, which is not that nice, but that's yeah, okay, it's really not that nice, but that's generated basically using PyGMT that can allow you directly to show your result on top of the heights, for example, of the hill shape. And you can generate also plots like this. And just wanted to end up by stating that there are more scripts in the LiCSBAS. There are scripts also where you can perform the decomposition. There were some questions about that. Yes, you can do it directly with LiCSBAS. The only thing you need is to have velocity estimated in descending, in ascending, right? And then there you will find for sure a script, there is not that many of them, that will perform the decomposition of the velocity. And here is a result of one volcano, where after decomposing that signal, okay, that's simplified because we are decomposing only the linear velocity here in this case. But this can be adapted also in LiCSBAS in parameters. And you can get into the vertical and eastward velocities, which is often where you want to get your final results to. So yeah, I will probably stop here, but I'm still happy to respond to any question. Let's say give it 5 minutes or depending on your hunger, because we probably have the promised pizzas there. So yes.
I mean, if you guys want to go, then that's fine. I'm not worried.
I am fine, but yeah.
It's more of a general question for someone that's not that experienced with Python. How easy is it to use this code to like look at our own areas of interest?
So okay, so fairly easy. Okay, so all those commands that I show here, these are okay. They are written in Python, but in Jupyter Notebook, when this is a, are you familiar with Linux?
Yeah.
Yeah. So these commands are just Linux commands. They would work in on the command line. Everything would start by the exclamation mark. Is actually only just running like in terminal. So basically, I can just open terminal and run those commands. So I don't really have to do anything in Python.
Yep.
Yeah, and you will generate, for example, the NetCDF file that you can work in any sort of tool that you are familiar with.
Okay.
So yeah, and maybe I should just briefly show the, yeah. So also the installation is also quite Python free. You basically do you can do pip install and that git repository, or just do the git clone and yeah, okay, that's other thing. But I wanted to mention about because the installation step, how to run the bash rc LiCSBAS, that's the only thing is described. Just go through it. That is wiki. It's easy. And just wanted to mention about batch LiCSBAS sh, which is something what we use that help the automatization fully. So I've showed you how to look into that procedure step by step. Yeah, that makes sense. Go through it at least once, once you get a little bit familiar with that thing, you can just set the parameters in the batch LiCSBAS SH. Again, that's shell script. Yeah, no Python needed. And you just set what you need from the number of loop to the various parameters. If you don't set anything, just give it a go. The standard parameters should be quite okay, and it should basically do everything needed. Yeah, and then you can just rerun some of the steps, particularly the LiCSBAS 15, for example, if you want just change the mask or whatever. Yeah, so yeah, that's just bash script for the Windows users. Yeah, I hear feedbacks that it works. You just need to again follow the Wikipedia that you can find a link to. There is information also from somebody who has experience setting LiCSBAS on Windows, which just means you have to install some.
Probably like a Linux subsystem, right? Like Sigwin, something like that.
Yeah. There is some application that basically replaces this.
I've got similar things.
Yeah.
Windows, so yeah.
Yeah.
So just to be clear, you're saying that we've ran the tutorial in Python just for kind of visualization and ease of access, but the best way to run LiCSBAS is in a Unix shell.
Yes, that's it.